Welcome to this introduction to compressible flow. We've got a couple of videos to show you to start to kind of motivate what we're going to be looking at. So let me get right into that. Here we have a bowl jumping into the audience. You see the audience scattering and staying away from the bowl until the bowl catches up to them. What does that have to do with what we see here in video 2? And finally, we'll show you video 3 here, which is very similar to video 2, just a different perspective. Alright, so 3 videos, 2 of them very similar. But how did the bull have anything to do with the flight of the planes here? Alright, so a bull represented by a circle here, so I don't have to. Oh, here you go, circle with horns. All right, so he jumped in the crowd, and the crowd initially was able to get out of the way until the bull got up to them fast enough, caught up to him so that they were right next to him. All right, and so that's what we have with compressible. Compressible flow is saying that the flow is going fast enough that the information or the people aren't able to get out of the way. The information isn't able to get upstream before the flow arrives. Or with a shock wave, the shock wave, you have no idea that the plane actually even passes you a little bit before you actually hear the shock wave. So you don't really know, besides what you can see, you don't know if the plane is there until it's already passed you, until the shock wave gets to you, which actually has a V pattern about the front nose of the plane. So that's what we're going to look into, and we're going to get more into that as we get into the rest of this presentation. So where are we going here? Well, we're in the midst of power systems, kind of following up on the gas power systems part. A little bit of fluids here, but we also have definitely some thermodynamics that's showing up in our compressible flow. But here you got the lay of the land and where we're heading to. All right, so let's start with the diffuser. And we're going to do an energy balance for our high-speed flow through this diffuser. All right, so just a reminder as we look at this diffuser, when we have flow going through something, the energy, we're going to have some internal energy, and we're going to have some flow energy that goes with that, and together they equal our enthalpy. All right, so if I did up from point 1 to point 2, and looking at an energy balance, I'd have H1 plus the kinetic energy component, so velocity squared at point 2, and that would all equal my enthalpy at state 2 plus the velocity at state 2 squared over 2. All right, so that's all well known, that's cool. But what happens if we would slow things down so the velocity at 2 would be 0? All right, so let's look what happens there. So H1 would still be plus, so we have some velocity at state 1, but then at state 2, it would be just H2, there'd be no velocity at state 2. So therefore H2 would be kind of a stagnation point. There would be no velocity. So we call that stagnation enthalpy. And I'm trying this to be 0 as opposed to look more like an O here. All right. So stagnation enthalpy. And actually, if you look at it, right, if we're saying this stagnation enthalpy is equal to H2, but it's also equal to this term over here, we could rewrite this top form here. H stagnation for point 1 is equal to the stagnation enthalpy at state 2. So it's basically these terms can combine to create a stagnation enthalpy term that's equal throughout the diffuser. It doesn't matter where you're at in the diffuser, it's always going to have the same stagnation enthalpy. All right, so that's going to be something important as we go through the rest of this presentation here. So we have some enthalpy upstream, like we looked at, and some velocity, and then the stagnation enthalpy that we just talked about. And we're saying, as we just highlighted on the previous slide, that the stagnation enthalpies are equal to each other as they go through. So this is a nozzle now, it's not a diffuser, but we still have constant stagnation enthalpy, this enthalpy of the stream plus the velocity that it's moving at. All right, and the way we can think about this is this plot. Now this is enthalpy versus entropy. And for an isentropic case, so if we had S1 equals S2, all right, an isentropic case, if it's slowed to 0, we would have this case here, and we have get this velocity term. So we have our initial h plus our velocity term here, and that would end up equaling our stagnation enthalpy. In reality, there's going to be some entropy increase, so we are going to shift over here, but we'd still have the same stagnation enthalpy. It would just be at a lower pressure. All right, so just keep that in mind as we kind of move through it. But again, kind of a visual perspective of what is this stagnation enthalpy. It's our initial enthalpy plus this kinetic energy component. All right, so stagnation temperature. Now, if we look in the case where we actually go to stagnation point, we hit a stagnation point where we take the velocity down to 0, and we do it adiabatically, so don't have to worry about any heat transfer. All right. We basically can take our equation, our enthalpy equation, and change it to temperatures. And so we get the stagnation temperature is equal to the temperature plus V squared over 2 times Cp. Okay, so that's our stagnation temperature is equal to the temperature of the flow, so temperature upstream. In this case, it would be 300 degrees upstream over here. This would be 300 degrees Kelvin. And then when we hit stagnation, when it gets to the point where it's stopped, it's increased 5 degrees if it was going 100 meters per second upstream. All right, so you take 100 meters per second down to 0 of a 300 Kelvin temperature flow, and it would increase 5 degrees. All right. Another equation that we can do, this could change into another one that's going to be we're going to use often, another form. Let me say it that way, kind of stumbling over myself. But to do this transfer, we're going to use the relationship between Cp and K, which is K times the gas constant divided by K minus 1. And what we'll end up with is the stagnation temperature over the temperature of the flow equals 1 plus K minus 1 over 2 times the Mach number squared. All right, now I'm going to come back to the Mach number, but basically it does involve the velocity of the flow, but we'll come back to that. All right, so again, some valuable terms that we'll end up using here with stagnation temperature. But what is a stagnation temperature? All right, let's go to a video to get an idea what's going on here. I'll watch the first part of this video. Again, I'll have the link in the description. You can kind of see it right there to watch the whole thing. And then I'm going to go to the long version of the same launch and to highlight some stuff. So here's the first video. So as you can see, it's a rocket, obviously. Very fast, very big rocket. So if you're used to doing model rocketry, this is several orders of magnitude more powerful than what you'll launch there. So I'm going to go over the long version, but it's going to be at a couple points that I want to highlight here. So as it's going up, this is when the video is going to start. So as it's already launched, it's in the air, and it's traveling along, and I'll tell you what's going on here. It's a camera looking back down. See, the stuff going by is melting plastic from the plastic camera's protective cover. Things get hot around Mach 3. Stagnation temperature is 804 degrees Fahrenheit. So what it's noting here is that the air temperature up at that altitude is pretty cold. We're talking below freezing. But yet the stagnation temperature, when you're going Mach 3, is 840 degrees. So it's melting the plastic cover for this camera. So let's see what the camera looks like afterward.
The lens,
All right, so you can see what's melted off and what kind of covered the lens in the previous video. So this part, the whole rocket's nice and nice cylinder, pretty much consistent the whole way down, except for where this camera is sticking out to get a nice view of the ground as it goes up. And you can see we got some melting over here as well. That may just be from this coming down on top of it. But obviously things get very hot, and they didn't worry about that too much. If they lost the camera, that's fine. At least the rest of the rocket returned fine. So that's a good visualization of what stagnation temperature can do. All right, now for some other stagnation terms, we got stagnation pressure, and this is on the handout. So sorry, by the way, I didn't say it at the beginning of the video. Link for the handout is in the description. So feel free to go ahead and download that if you wanted to follow along. All right, so but stagnation pressure is in this form here. So again, it's just basically manipulating over from what we had for the stagnation temperature using ideal gas. We also can use this form, again, doing the same transfers we did before, going from stagnation temperature in the two different forms, but getting in a form of Mach number, which is really convenient for a lot of the analysis that we'll do, analyses. Stagnation density, again, same process that we did for the pressure. And finally, just to highlight the Mach number, if you're not familiar with, the Mach number is the velocity of the flow divided by the speed of sound in that flow or in that fluid. So if it's air, it's the speed of sound in air. If it's water, it's the speed of sound in water. So you got to be careful about which fluid you're going through. But for what we're going to be using this in this analysis, using ideal gas, the speed of sound we can calculate from kRT. So gas constant, or sorry, specific heat ratio, gas constant, and the temperature of the flow. All right, so that's it for this video. The next video, check out, I'll be going through this example, basically just using these equations, plugging in some terms, and seeing what we can develop, looking at how the overall temperature, pressure, density changes through this nozzle. All right, and there's a couple more videos after that. So again, stick around, and hope you enjoy it.